I want to dabble in this idea of neutron stars a little bit more. Kind of explore in this last section some of the mysteries of the universe, if you will. In 1967, Jocelyn Bell discovered something that was pulsating out there far away. And as she thought, gosh, this is pulsating so regularly that maybe it's some sort of intelligent life. And so, honestly, for a little while there, they actually thought it might be a message from space. So she called the star LGM-1 for Little Green Men. Well, it turned out, obviously, not to be intelligent life, but Bell was able to describe the first neutron star that was rotating, causing a pulsating. I'll show you how you get the pulsations in a minute. And so this pulsating radio star was then referred to as a pulsar. All neutron stars that start out rotating, they will increase in their velocity, or all stars that are rotating and that go to form a neutron star, when they collapse, they increase the speed. It's sort of like a figure skater with the arms out and then moving their arms in, and that forces them to spin quicker. And the same kind of idea is existent with pulsars. And in this particular diagram, the pulsar is spinning around the green axis that you see there. And the reason that these things pulsate is that we believe that there is a strong magnetic field around them which forces all the energy to come out the north and south poles of these neutron stars. And you can see in the Vela pulsar there that looks exactly what is happening. You can see the rays coming out. And then if you're viewing from the Earth and you are looking at the part of the neutron star which has the poles and the energy coming towards you, then you'll see it pulsating because it's revolving. I got a little video here which just shows you how you can get a pulsating star based on the fact that the energy is coming out the north and the south poles. And there seems to be hundreds of millions of these neutron stars in our galaxy, and you can see them if you happen to catch the view from where the energy is coming out of the poles and it's facing towards Earth. There's a neutron star in the Crab Nebula, which you may remember seeing. That neutron star there, it's pulsating, actually rotating at 1,980 times per minute. So it gives you an idea of how fast these things go. And they're emitting lots of radiation, gamma ray radiation too. They also make superb clocks, with the best clocks ever in the universe. In fact, we just had an atomic clock made recently that turned out to be better than a pulsar. Well, everybody's interested in black holes, and so I feel like I need to talk about black holes. If you have a neutron star, if the star starts out big enough, maybe greater than 16 solar masses, then instead of ending up with a neutron star, it's going to collapse further into a black hole. Now, what do the equations tell us? Well, the equations tell us that mass is going to collapse into the center and go to zero. And that's what the equations tell us. Nobody knows what happens in a black hole because no one can go into a black hole and send back any information, because as we're going to find out, anything that goes into a black hole can't come out because the gravitational pull is so great. Even light. So if light gets trapped in a black hole, the light can't get out even. And so that's what's called the event horizon. If you get beyond the event horizon, nothing's going to be able to escape. And you know, if you were approaching a black hole, I want to emphasize that it's not like there are going to be signs up saying, you know, warning, event horizon ahead. the point I'm trying to make is that you wouldn't know that you were in an event horizon, except that if you turned around and you tried to get out, you wouldn't be able to get out because you couldn't travel fast enough. Even light can't travel fast enough to get out if it goes beyond this so-called event horizon. And this is also called the Schwarzschild radius, named after the man that actually made the calculation for what how to determine the event horizon based on the original mass that was put into the black hole. Now, I don't want to mislead you here. In the sense that you can't make black holes on Earth. But if a black hole had the mass of an Earth-sized object, it would only be about 8 minutes, 8 light minutes across. So we're not talking about a lot here. That would be its event horizon. I mean, that's how long the sun light takes us to reach us here on Earth. So we're talking about not a great distance. So these black holes and the size of the black holes depend on how much mass you start out with in the first place. Now remember, I told you before that quasars are probably super giant black holes that are sucking in these super galaxies into the center of them. In fact, the bulges on most of these disk galaxies are probably formed by the clumping together of mass going into black holes. So we know that black holes are out there. We've been getting gamma ray bursts across the universe, been documenting them for a long time. And finally, we have some evidence to suggest that these are formed from the formation of black holes. So there's some evidence right there that gamma ray bursts are generated, and it turns out that they're associated with supernovae. So maybe what we have is a neutron star collapsing or neutron-neutron stars interacting. But whatever it is, we're seeing these gamma ray bursts, and we believe the gamma ray bursts are caused by the formation of black holes. So there is some ancillary evidence for the creation of black holes out there in the universe. It turns out that probably our best example of a black hole comes from Cygnus X1. Now, Cygnus X1 is rotating around something in the sky, but we don't know what that something is because we can't see it. Well, that's just what you'd expect from a black hole. But it's rotating, and we can calculate how fast it's rotating, and it turns out that the mass is about 15 times the mass of the sun, maybe larger. So it's rotating around something very dense. So we're about 99%. I say we. They're about 99% sure that there's a black hole there. I don't know if you saw the movie Interstellar or not, but I not only saw the movie, I read the book, and the book's by Kip Thorne, and he talks about, he was involved in the ideas in the movie, and then he was hired also to make all the calculations. He's an astrophysicist at Caltech. He made all the calculations to show us what black holes would really look like if you went into one. So if you ever see that movie, or if you have seen it, then you know probably what a black hole would look like if we could go into it. So it's really interesting because it's based on actual calculations and the actual physics. So if you get a chance, go back and take a look at Interstellar. It gives you a pretty good idea of what these black holes look like. Well, I want to talk a little bit now about the center of our galaxy. We think there's a black hole in the center of our galaxy, and one morning somebody just didn't wake up and say, gosh, I bet you there's a black hole in the center of our galaxy. It's taken a lot of measurements, a lot of data has been collected, and I want to show you this video here. It's a video of data that's been collected by looking at the center of our galaxy. Now, we're shifting to longer wavelengths here, so you can see through the dust in the center of our galaxy. And we've measured the stars in the center and their motions over the last 15 years. And so we can take those stars that we've looked at, and we can model them. And what we're seeing is that they're going around some sort of point in the center, and we can't see what that is. So a very good idea that it is a black hole. Now, how much mass is necessary to generate the speed at which those stars are rotating around that center of our galaxy? Well, it turns out, and this is almost unimaginable, turns out that the mass is about 1,000,000 times solar mass. So, wow, you're getting 1,000,000 times the size of the sun in that black hole, and it's about the size of a few light hours. So, to put that in perspective, that's about the distance from the center of the sun to Pluto. So you're putting 4,000,000 stars, the size of the sun, into that distance, and you're getting this black hole, well, at least what we think is a black hole, as the result. Well, we are now at the point where we can do some summary of the history of our universe. I want to emphasize that you know, human beings have been in civilization now for about 10,000 years, and this is the first time we're living in a time when we can know how old our universe is. Just think about that. We know that our universe is 13.8 billion years. Well, it is just kind of unimaginable to me that we can even understand that. But it's taken hundreds of years of very bright people studying the sky, and now we finally have some answers to these what were thought to be imponderable questions. This is the universe, 13.8 billion years, the history really of the universe, and if you could do it in one slide. You see that we're looking over the visible universe, and if we start at the Big Bang at 0, we went through a period you know, of quantum fluctuations. That's what broke down the universe into those variations, small variations as they were. They were enough to clump matter together because gravity was able to take over after energy and mass separated. And that happened about 380,000 years ago, as we mentioned, from the fog. And then we had the breaking down of the forces. We talked a great deal about the forces. They all, it's believed, started out as one in the theory of everything. And then gravity broke out, and then as the universe cooled a little bit more, we had the grand unified theories, which tells us that that the strong force broke out. And then finally, they cooled enough to where we have the electroweak and weak forces, electromagnetic and weak forces breaking out. And so we have 4 forces today because of the cooling off and the breaking out of the forces. And then at about a microsecond, the quarks come together to form protons and neutrons. And then after a certain amount of time, we start to get some nuclear fusion. Remember that we're probably about 90 seconds into the process before we can get neutrons stable to form deuterium. And then deuterium can go on to form helium. And remember, we've only got I think about 887-second half-life there for neutrons outside the nucleus before they start decaying. Gives us 7 half-lives, so we got to do that pretty quickly before all the neutrons go away. And that's precisely why we don't have any more elements bigger than helium in our universe. So something to keep in mind. I mean, any bigger than helium as created by the Big Bang. Obviously, we've created them through a nucleosynthesis of stars. Well, then the next step was, of course, the cosmic microwave background radiation was able to escape from the fog. It stopped running into the neutrons and protons once they formed atoms, and the electrons stabilized the atoms. So that now, about 380,000 years ago, or after the Big Bang, I should say, we started getting these photons running wild through space. And you know, I have to emphasize, if you look back with telescopes, you run into this big wall out there of fog that represents the beginning of the universe, and we can't see through that. So there's a limit to how far out we can see because we're looking back in time. And we actually start to see galaxies near that fog that we're forming, so we can get back that far. And also that tells us that galaxies were forming very early in the evolution of the universe. And of course, since the formation, the clumping together of mass, we've been able to get galaxies. Those galaxies have gone on to form supernovae and red giants, and they've dispersed elements throughout the universe. So stars that are many generations after these events of nuclear synthesis, we get to form stars like our sun 4.5 billion years ago, which are full of elements that you can get to form human life. And so that's where we are. Pretty much a history of the universe done. There's still some unknowns, as I've mentioned, lots of work to do, but we're on our way. And I think you're living in a very special time, a time when we can, scientists can pontificate about all these wonderful discoveries that have been made based on copious amounts of evidence.